Next chapter, effects of heat on substances. Now, heat is a form of energy. Heating brings about a change of state, a change in volume, and chemical changes. The most obvious effect of heat on substances is the change of state. When a solid is heated, it melts and converts into liquid state. Equally, when a liquid is heated, it vaporizes into gas. When a solid, liquid, or gas is heated, it usually expands, thus increasing in volume. Observe a balloon that is tied over the mouth of the bottle, filled with boiling water. The balloon gets inflated due to the expansion of air, showing a change in volume. Certain substances undergo chemical changes when heated to form new substances. The behavior of matter in response to heat can be explained by the kinetic theory of matter. The kinetic theory of matter forms the basis of the theoretical model of matter. According to this theory, all matter is made up of tiny particles that are in a continuous state of motion. The motion occurs because the particles possess kinetic energy, which is the energy of motion. The larger the kinetic energy, the more the movement. Particles in solid state are tightly packed together in a regular repeating pattern, leaving very little space between them. The kinetic energy of the particles is very small. The forces of attraction between the particles are very strong, and the only movements they make are tiny vibrations to and fro. This is why solids are rigid and have a definite shape. If a stone is placed in a box, it does not change its shape. When a solid is heated, the heat supplied increases the kinetic energy of the particles, making them vibrate more. At a temperature called the melting point, the kinetic energy is large enough to weaken the forces of attraction between the particles and acquire some level of freedom. The solid melts into liquid. In the liquid state, particles are closely held together but are not in a fixed pattern. Rather, they move freely and have a greater space between each other. Because of this greater space, the forces of attraction between the particles are weaker than in the solids. The kinetic energy is large but not sufficient for absolute freedom. This is why liquids have definite volumes but no definite shape. When the liquid is heated, the kinetic energy increases, making the particles vibrate more until they overcome the forces of attraction and break loose. The liquid boils into vapor. Matter in the gaseous state has no definite shape nor volume. In the gaseous state, the particles are far apart. There is greater space between the particles and they move about randomly with infinite freedom. Due to the huge spaces between the particles, there are no forces of attraction. Now, the kinetic theory of matter can be supported by several observations. First, since the particles in matter are in a state of motion, it means there exist spaces between the particles. We can prove this by using the example of salt dissolved in water. When salt dissolves in water, the particles of salt get in between the spaces between the particles of water. You will know this because there is no change in volume of water. This confirms that the particles have spaces between them. Another important feature is compressibility. If we take 3 syringes and close the mouth of each syringe with a cork, we fill one syringe with chalk powder, another with water, and leave the other empty. We insert a piston and try to compress the material inside the syringe. You will see that the syringe with solid is not compressible because solid particles do not have enough spaces between them. The syringe with water is slightly compressible because there is some space between the water particles. The syringe, which is empty, is easy to compress because the particles in a gas, that is air, have very large spaces between them than in solids and liquid. Another proof is diffusion. When a perfume is released in the air, the fragrance spreads very fast. This is because the gaseous particles in the perfume moves very fast in between the spaces between the particles of air. Liquids have slower diffusion rates because the spaces in between the particles are smaller than those in the gases. In solids, diffusion is negligible because the spaces between the solid particles are extremely small. In fact, a solid cannot diffuse through another solid. So now, let's go back to the effect of heat on substances, and the first effect is change of state. We start with an experiment to observe the change in temperature during heating. Now, we take some ice cubes in a beaker. We suspend the thermometer into the ice cubes and note its temperature. It's 0 degrees Celsius. Then we heat the ice cubes and record the temperature after every minute. Keep stirring the ice-water mixture constantly so that the temperature is uniform throughout. We observe that the thermometer reading remains constant at 0 degrees Celsius, though heat is being supplied constantly. The temperature remains constant till all the ice melts into water at 0 degrees Celsius. Continue heating the water. We observe that the temperature is increasing. Record the rising temperature till the water starts to boil. Continue heating. The boiling water gets converted to steam. Observe that the thermometer reading remains constant at 100 degrees Celsius, which is the boiling point of water. That is, there is no change in temperature. This experiment shows that temperature remains constant whenever there is a change of state. But what happens to the heat energy being supplied? The energy supplied is used to break the intermolecular forces of attraction between the particles, and therefore there is no increase in temperature whenever there is a change of state. If we draw a graph of temperature against time, we will obtain this curve. At region AB, the temperature remains constant until all the ice has melted. The heat supplied is used to weaken the intermolecular forces of attraction between the ice particles. This temperature is called melting point. At region BC, the temperature rises steadily as heat energy supplied causes an increase in the kinetic energy of the particles and thus makes them move faster. In region CD, the temperature remains constant again until all the water is converted to steam. The heat supplied is used to weaken the forces of attraction between the particles rather than increase the kinetic energy of the particles. This temperature is called the boiling point. All pure substances have a constant and specific boiling and melting points. Impure substances do not have constant boiling and melting points. For instance, if we take 2 cups of water and put a spoonful of salt in one of the cups, and then we place them in a freezer and check on them regularly, we will see that the water without salt freezes fast. The reason is that salt lowers the freezing point of water, which is also the melting point. In general, impurities lower the melting points of substances. They will raise the boiling points of substances. If we plot a graph of temperature against time for heating salty water from ice, you will see that the salty ice melts over a range of temperature below 0 degrees Celsius. The liquid salty water boils over a range of temperature above 100 degrees Celsius. And this is why during winter, salt is poured on roads. This way, the freezing point is lowered and snow can only form at very low temperatures, and the already formed snow is melted. Also, because of their salty nature, ocean waters do not freeze during winter, and yet fresh water streams and lakes freeze. Salty water therefore freezes at very low temperatures that are usually not reached during winter. And so in summary, any substance can go from one state of matter to another by changing temperature. These are physical changes, not chemical changes. Remember, all these particles are moving. They have kinetic energy, which is the energy of movement. Solids have the least kinetic energy. Liquids have more, and gases have the most. To change the state, you can alter the temperature to get the desired state of matter. To change from solid to liquid, you add energy to melt it. But to change from liquid to solid, you remove the kinetic energy by decreasing the temperature, and that's freezing. Similarly, a gas can become a liquid by lowering its temperature and condensing it. When a liquid's temperature increases enough, it can vaporize to become a gas. Some solids can skip the liquid phase and go directly to gases when we increase temperature. This is called sublimation. Gases can also go directly to solids in a process called deposition, which is also called desublimation. Now, this kind of organization makes for a beautiful chart, but it doesn't show how adding energy makes the difference. We can adjust the chart to look this way. And this is the order of increasing energy. And it could be more specific if we write increasing kinetic energy. Now let's continue with other effects of heat on substances. Different substances undergo different changes when subjected to different conditions of temperature. In this last part, we classify these changes. First, temporary physical changes. Consider zinc oxide, which is a white solid, when cold. When we heat the solid, it turns yellow in color. When we leave it to cool, it turns white again. Heat again, it turns yellow. Leave it to cool, it turns back to white. Now, this kind of change is temporary and physical because only the color changes. The compound remains zinc oxide. It is a temporary physical change and can be represented by this equation. Other temporary physical changes include heating ice and iodine. Temporary physical changes have the following characteristics. There is no new substance that is formed. The process is easily reversible. There is no change in mass, and there is no net change in heat. Next is temporary chemical change. Consider hydrated copper 2 sulfate, which is a blue solid. It is called hydrated because it has water of crystallization. When the salt is heated, it loses the water of crystallization, and you will see it gradually turns white in color. Here we are. This white solid is called anhydrous copper 2 sulfate. If we add water to this white solid, it turns blue, so back to the hydrated copper 2 sulfate. Cooling does not reverse the reaction. This reaction can be represented by this equation. This is a chemical reaction because 1, a new substance is formed that is anhydrous copper 2 sulfate. Heat is absorbed during heating and evolved during the addition of water. There is a change in mass, that is, the hydrated salt is heavier than the anhydrous salt. It is, however, a temporary change because it can be reversed by simply adding water. Another example of a temporary chemical change is the heating of hydrated cobalt 2 chloride. The last type of change is a permanent chemical change. This makes the vast majority of chemical reactions. Here, new substances are formed. The change is irreversible. There are changes in mass, and the reactions are accompanied by energy changes. Let's consider the thermal decomposition of copper 2 nitrate. Some solid hydrated copper 2 nitrate is heated in a test tube. It first dissolves in its own water of crystallization, and then the solution boils. A brown gas is produced, which turns a wet litmus paper red. When a glowing splint is inserted, it relights. At the end of the heating, a black solid remains. The reaction that took place can be shown by this equation. And so, throughout the study of chemistry, you will encounter numerous reactions. And really, you should be able on your own to identify the type of the reactions that they are.
It's important to mention that ancient civilizations weren't just big doers, they were also big thinkers. While the Indians were mastering steel, philosophers in ancient Greece, like Democritus and Aristotle, started asking questions of how nature is put together. Many consider Democritus to be the father of modern science. Democritus and his mentor Leucippus developed the idea that everything is made of atoms, an infinite number of indestructible units of all shapes and sizes that have always been, and always will be, in motion. Some modern historians and scientists say Democritus simply got lucky, and recent evidence just happens to confirm his hypothesis. But the Greeks weren't that thrilled with Democritus either. Rumor has it that Plato, another thinker of the time, wanted all of Democritus's works burned. Plato thought Democritus was too materialistic, that ideas ruled the universe. Democritus and Plato, the Hamilton and Jefferson of their day. But like some sparring heads of state, parts of both their ideas contributed to the formation of science. Though, after several centuries, it turns out Democritus was more correct with his atomic theory.